Okay, so here's another problem. This time it says slope and displacement. I don't know if we'll have time to do the slope. I may have to pick that up with you next Tuesday. Is that April Fool's Day? No, April Fool's is Monday, isn't it? If you get an email from me with anything important on April 1st, you might want to ignore it. Okay, anyway, so here it is. So let's focus on the displacement at C right now. You can see if you want to do direct integration, you would have to write two sets, and you'd have some simultaneous equations to solve to match for the constant. If you want to do conjugate beam, this isn't a bad conjugate beam. The fixed connection becomes free, the free becomes fixed, so it's a cantilever beam. But what kind of moment would this produce? It would be parabolic shaped. It might be a little tricky to find that depending on what you wanted. I think it would work for this problem because we're trying to find the displacement at C, which in the conjugate beam would just be a reaction to the total load. You'd probably be okay. So let's see how it compares to virtual work. So just like we did before, we're going to have to write a real expression for the moment in this beam, and you can see due to the discontinuous load that I'd have to write one moment expression that would be valid over the first 7 meters and a second over the next 7 meters. So looking at the first section, I make a cut. Do you want to work the left side or the right side? Now it gets a little more challenging because if I did work the right side, I wouldn't have to find any reactions. If I worked the left side, I'd probably have to find some reaction. So what amount of work it is, I don't know. I'm going to do the right side, so I'm not going to find reactions. When I cut it between B and C, then I'm definitely going to use the right side, because that one's way easier. So the cantilever beam does offer you an option to usually look at the free end side or the other side that has the reactions. The reactions would not be hard to do, but that would be additional work. So let's just do the right-hand side for each of these. So let's look at the real moment expressions in this beam. Now, if you're thinking back about way back in the first part of the course, I think I gave you this problem, and all I asked you to do was find the shear force and bending moment equations. That was the whole problem. Now that's 1/3 of this problem. So you guys are getting more skilled every day. You're getting your money's worth. I know I earlier told you that you should file a class action lawsuit to seek repayment, but I think you're really getting your money's worth. We have to argue that in court, but I think you're learning. That's what counts. All right, so let's look at the first one, which is going to be valid from x equals 0 to 7. And I'm going to cut my free body diagram. I'm going to look at the right-hand side. I know out here at the end, I have a 75 kilonewton force. And then I'll have some portion of this remaining. That has an intensity of 25 kilonewtons per meter. So I'm going to come up here and at some distance x, I'm going to have to figure out all these other pieces. Well, I know the total length is going to be 14 minus x. And I know this little segment here is 7, right? From here to here. So the geometry is a little bit more interesting. And then, of course, I'm looking for the real moment at that cut. So let's find that. So I'm going to sum moments at the cut. Make sure it's in equilibrium. So what do I have? Well, starting here at the cut, that moment with my sign convention is negative. Now I've got this distributed load here, right? I got to make a concentrated equivalent force of that. What would it be? What's the area under this curve? It would be base times height. What's this base distance? If this is 14 minus x, and you subtract 7, you get 7 minus x. So the base is 7 minus x. The height is 25. That force is going to be down and create negative moment. So negative, the force is going to be 25 times 7 minus x. And what's going to be the distance from the cut to the centroid? 7 minus x divided by 2. So this looks a little strange. But that will lump together pretty quick. And then what else do I have? The 75 out there on the end, and that's creating a negative moment. And that has a moment arm of 14 minus x. So when I solve for the moment, what am I going to get? I'm going to get negative 25 over 2 times 7 minus x squared minus 75, 14 minus x. Do I know the moment anywhere from 0 to 7? Answer is not offhand. I would know it at x equals 0. That would be the reaction moment. But I didn't solve for that. So you don't have that in your pocket. If you do put in 0 here, you can actually calculate that moment. It looks like it's going to be negative. At least it's the right sign. So there's a little disadvantage. If we had worked the left side and we have to solve for the reactions, then we would know our equation would include that. I feel pretty good though. I think that's accounted for everything. And you don't have to do anything with it. You can just leave it like that if you want. Now what else do we need to do? We need to go from 7 to 14. In that case, I'm just going to cut the little free end off. That would have 75 kilonewton force. So our x comes up to the cut. And the remaining piece would be 14 minus x. And then we would have the internal moment. I probably should have underlined those so that you can see and they stand out a little better. And that's not too bad. So we'll sum moments at the cut. It's equal to 0. So what do we get? Well, that's a negative moment. The 75 kilonewton force creates what kind of moment about the cut? Positive or negative? Also negative. So we'll have 75 times a distance of 14 minus x. So it looks like the moment there is negative 75 times 14 minus x. Now, do we know the moment there? Anywhere on that section? From 0 to 14, do I know the moment anywhere? What's the moment at the free end? 0. So if I put in x equal 14, what do I get? 0. Okay, that's good. So I like that. So I know the moment at x equal 14 should be 0. And my equation gives me that. So that's good. And what else should I know? These two expressions should give the same value at x equal 7. So what is this one at x equals 7? Somebody compute that. Well, this term is going to cancel out, right? This is going to be 7. What's 7 times 75? 525? And that should be kilonewton meters. And then what is the moment here?
I think it's negative.
Oh, it is negative. Thank you. And what is the moment here at x equals 7?
Negative 525.
Whoa! Yes, I like that. So I would give that a double green check. I'm pretty confident that my moment expressions are good. So let's do the virtual beam. No R there. So what does it ask for? It asks for the displacement at C. So I'm going to draw my original beam. And I want the displacement at C. C is the free end. So just like we did before, I'm going to assume the force is acting up to match my sign convention. And that's 14 meters. How many equations do I need to write for that? 1. So if I cut this beam in the middle, you want to work the left side or the right side? I'd say the right side. I don't have to find my reactions. So now this equation is going to be valid over the whole length of the beam. So I'll cut my structure at some distance x from the left-hand side. That will leave me a segment that is 14 minus x long. And we have our virtual force of 1 acting up. So what I'm looking for now is my virtual moment in the structure. So again, I'll sum moments at the cut, make sure it's in equilibrium. And what do I have? Well, the internal moment is negative. The moment created by this virtual force about the cut is positive, and it has a value of 1 times 14 minus x. So it looks like the virtual moment is equal to 14 minus x. Does that work? What's the moment at the free end? 0. So the virtual moment at x equal 14 should be 0, and it tells us that. And obviously, if you put in x equals 0, you find that the real moment is 14. And that makes sense. 1 times 14 meters should be 14. So the last thing I have to do is piece these things together. So now, if I want to find the displacement at C, I'm going to integrate the real moment times the virtual moment divided by EI. And normally it would be between 0 and 14. Now, my virtual moment does go from 0 to 14, but my real moment doesn't. It goes from 0 to 7, and then from 7 to 14. So I'm going to have to break it up into 2 pieces. The first piece, I'm going to factor the EI out just to save me a little space. So I'll factor my EI out to the outside, and then I'll have the integral from 0 to 7 of the real moment, all that stuff. I guess I'll just write it. Minus 25 over 2, 7 minus x squared minus 75, 14 minus x. So that's the real moment. And the virtual moment is 14 minus x. There's the first piece. And then the second piece from 7 to 14 would be, this is my real moment, minus 75, 14 minus x. There's the real. And the virtual is 14 minus x. And for me, that's the solution to the problem. Yeah.
Is that the plus, right?
Say again?
The plus.
I got a sign. Oh, I did miss a sign there. Thank you. So I'll do the same thing. I'll go back to the office and I'll put all the values in and make it come out. But that's good enough for me. And that only took 14 minutes. All right.